In the last class, I had talked of elements of spray pyrolysis, and I had stopped at this particular diagram where I said this was one of the droplets injected into flame. I said as it enters, water can evaporate uniformly due to the very high steep rise in temperature, leading to volume precipitation and finally a product. Whereas it is possible that surface precipitation can happen, and in that case I said it could form either this sort of an open product or this sort of a closed structure with an empty core. Now let me focus today as well as start on this particular process. Volume precipitation can lead to co-precipitation. You see, first of all, this process is very amenable to co-precipitation as the delta, the temperature is very high. Water is being injected into a flame here at 1800, 1700 degrees centigrade. The water evaporates, the solution gets concentrated very fast, and normally what we get is a co-precipitation. So at this step, if I blow this up, this is the same diagram I am blowing up on a microscope. What I would see is very fine nuclei forming. Very fine nuclei forming. Now, because this flame is at a very high temperature, 1700, 1800 degrees centigrade, the advantage of this process is this, that if we take, say, a mixture of magnesium nitrate solution plus aluminum nitrate solution and spray pyrolyze, due to the steep increase in temperature, very high temperature, and also very small surface area of the droplets, both magnesium nitrate and aluminum nitrate, they decompose in the gas phase. And magnesium nitrate, aluminum nitrate, they decompose in gas phase, giving you MgO plus Al2O3 in gas phase, and they react to give you MgAl2O4. However, again, it is not as if all these particles over here will be comprised of MgAl2O4. If I look at the microstructure of this particle after complete spray pyrolysis has occurred, what I would see is, if I blow it up still more, that is, I am blowing this small grain up into this, I would see each grain is MgAl2O4. So this is the grain, and it is polycrystalline and has got MgAl2O4 with green boundaries and all of it. At times, what we do get are very dense grains, just as I have drawn right now, very dense grains, MgAl2O4, all of them are MgAl2O4, but at times we get very porous grains also. We get very porous grains also. This depends on the type of gas evolved, the temperature at which it has been pyrolyzed, the speed at which the solution or the droplets have been put in the flame, and this process of injection of droplets into the flame, the atomized size, all have to be considered and balanced if we are going to get a very, very dense structure. At times, what we have to face the problem is this sort of a growth occurs if we have the two species AO and BO either yielding very high amounts of gases or they have very high solubility, very different solubility. In that case, we get very, very porous structures. In such cases, what we could do is, say as I had stated earlier, we could precipitate nickel ferrite or barium titanate, as I said in last lecture, by adding oxalic acid because they precipitate. But I said magnesium aluminum oxalate, they do not precipitate, they are very highly soluble. What we could do is to get very dense fine particles, we could form a complex, like say a very highly in product which is being investigated for the semiconductor industry, and it is a ceramic, is lanthanum calcium manganate. It is got 3 cations. It is very difficult to precipitate by co-precipitation process, and the only way to deposit what has been found is spray pyrolysis. What they do is they take lanthanum nitrate, calcium nitrate, I am writing magnesium nitrate, but magnesium nitrate per se is not stable, dissolve, add oxalic acid to form a complex solution or a complex solution. This is used for spray pyrolysis. And it is being investigated by semiconductor industry to replace electrical contacts which are now metals in semiconductors as they go down to nanometer level technology. They are in the semiconductor industry, lanthanum calcium manganate is being spray pyrolyzed to deposit thin films of lanthanum calcium manganate. It is a one-step process, unlike other processes, and it is proving to be very effective. Many parameters are yet to be controlled, modeling is being done, because here, for those of you who have taken ceramic technology, you know manganese can exist in different valence states. Manganese is 2+, 3+, 4+, and depending on the valence state, its conductivity will change. So, we need extreme control on the valence state of manganese. So, in this particular case, we have to balance the oxygen content, the spraying rate, the temperature to get reproducible films of lanthanum calcium manganate. So, in addition, so spray pyrolysis to finish it off can be done using salts, or rather solutions of salts, using organic complexes which keep the metal ions in solution. When I use the word organic complexes, we are always looking for simple organics. The choice is oxalic acid. This is the best as it burns cleanly, leaving no carbon. Another one that we have used successfully is citric acid. Both of these are carboxylic acids. As a result, a cation, one type of cation can be bonded here, the other type can be bonded here. Now, this is a vast area of spray pyrolysis, and especially today in thin film deposition, where we are talking of deposition of multi-component systems. Lanthanum calcium manganate was only one. There are various other spintronic materials which are multi-component systems. They are being deposited in thin film form by the spray pyrolysis route. The thin film form deposition will be taken up later, but I brought up the word of spray pyrolysis to tell you that by this method we can deposit very fine sized multi-component oxides from the solution, which are difficult to synthesize by either solid state route or the co-precipitation route. While I am still on the subject of preparing value added components or oxides from solution, I would take up now another process of making powders from solution. This process was again invented by the Germans back in 40s, when they manufactured Vicor glass. Actually, during Second World War, the Germans had a problem of raw materials. Quartz was an essential component for the war machine because it transmits ultraviolet light. Unfortunately, that means very, very high purity silica. And the Germans had almost no access. That is when they invented the process of Vicor glass. It's true, Vicor was not as transparent as quartz to ultraviolet light. Quartz is transparent up to 196 nanometers in vacuum. Y-core is transparent up to 220, 230 nanometers in vacuum. Yet, at those times, they needed the mercury vapor line to be transmitted. 254 nanometer, the low pressure mercury vapor lamp. And the Y-core glass offered an excellent alternative to quartz. This process was rediscovered in 50s and 60s and is a very technologically important process today. Let me take one system. Why is it called? What is it? Let me talk of it. The starting material is TEOS, tetra ethyl orthosilicate. It means silicon these are the ethyl groups, and this is because there are 4 such ethoxy groups. It is called tetraethyl orthosilicate. Now, for brevity's sake, because in future drawing such complex diagrams is difficult, this particular group I shall refer to it as ET, ethyl. So, I have here got 4 ET groups. I have got 4 ET groups. I will abbreviate this to as SiOET, OET, OET, OET. This is how I shall abbreviate this compound. In case I am writing SiOMe, OMe, 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 it means Me stands for methyl group, CH3. So, instead of Me, I could have written here CH3, 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 CH3. So, with that small thing, this is tetraethyl orthosilicate, this is tetramethoxide, and the other groups I shall bring in as it comes. Let me draw the flow diagram first and then explain the mechanics of the process. Let us say we will take 50 ml tetraethyl orthosilicate in 100 ml water. Let us add as a presumptive value 100 milliliter 50 ml ETOH or ethyl alcohol. This is CH3 CH2OH, and 1 drop of 1 normal hydrochloric acid. What we will do is, we will take it in a round bottom flask, put it in a heater, this solution will be over here. This will be fixed to a refluxing tube, this is a refluxing tube. Water can flow in. It flows in this jacket. What happens over here, when we heat this, this boils. The vapors go up, they condense over here, and they fall down. So essentially what is happening is, over here I am boiling the solution, the vapors are going up, they are recondensing, so there is no loss of liquid at all. And during this process, remember I have added HCl acid. Let us see what is it that happens. During this process, what happens is, hydrogen ions OH minus, they attack. This allows formation of, this is the basic hydrolysis step. Protonation occurs over here. This causes the liberation of ethyl alcohol, which is liberated, and OH. Now, during this distillation process, repeated hydrolysis occurs. So, what happens is, we have a polymer chain developing. Much like your polymerization process. This sort of polymer develops, and what we have is, not only I have drawn a single chain, polymerization can also, or does also occur in all the directions. So, you can have a very network structure if you let the polymerization go on. But normally what we try to do is have linear polymer. We avoid polycondensation so that we have got SiO, 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 SiO fibers or chains rather. Now, I come back to this diagram. I am refluxing. This process is called refluxing. Depending on the relative amounts of tetraethyl orthosilicate, ethanol and the water, the time for which refluxing will occur will vary. One has to stabilize these conditions. What I would do is, after refluxing, it will be poured into a Teflon beaker, and what would happen is, under a microscope you would get a very clean solution. If this is the level of the liquid, you would have polymeric chains of this particular material all over it. Now remember, this is not viscous. You see, this is still has the viscosity of water. Why? In this refluxing process, we did not let any water evaporate. As a result, what has happened is the amount of the solvent content has stayed fixed. And one thing more, why did we add ethyl alcohol? The answer is very obvious. You see, at ethyl alcohol is a reactant or is a product. We added ethyl alcohol to slow down the reaction rate. That is why, because we added ethyl alcohol, we got a linear polymer. Otherwise, polycondensation could have occurred. So the role of ethyl alcohol here was also to control the hydrolysis rate. So I come back here. When I pour the material into a Teflon beaker, I will have plenty of polymeric chains in this solution. If it is allowed to dry in air, the water would the solvent would evaporate, the chains would get very dense, and this can become now a hard gel, very hard gel. This gel has been derived from TOS. So it is called alkoxide based gel. This gel can be fired to yield the desired product. Now, in this particular case, I started off only with TOS, tetraethyl orthosilicate. So here I would get silica. What the Germans did for the Vicor process was they took this gel, dried it carefully so that it did not crack during drying. You see, I had said this was a Teflon beaker. I had written it was a Teflon beaker. The reason I had used it as I used Teflon beaker was so that when the gel dries from here to this shape, it does not stick to the walls. If the gel sticks to the walls, what I would get is something like this. This sort of a shrunk gel. This would be under very high tensile load and this would crack. Rather, it is best that it be taken in a Teflon beaker where there are no surface forces and the gel shrinks uniformly. This is exactly what the Germans did. They dried it very carefully, and it was not only Teflon beaker by using to reduce adhesion, but secondly and most importantly by controlling the vapor pressure in space above solution. This is very important. Let me redraw the diagram. This is a Teflon beaker, and this is a solution level. That is hydrolyzed solution, that is after refluxing. This has water and ethyl alcohol. You know ethyl alcohol evaporates very fast. Alcohol, water, ethyl alcohol evaporates very fast up to its eutectic point. So, if this is kept open to air, what would happen? The ethyl alcohol or the eutectic solution of ethyl alcohol, water, would have evaporated very fast. As a result, at the next step, what would I see? That water is evaporated, true. The gel volume has decreased, true. But this surface, the top surface, is under very high strain. This area just below the surface will be much drier than this area. As ethyl alcohol water has evaporated from the surface very fast, yes, the solution has got concentrated, and at one point of time what has happened, a thick scum, like say when you warm milk and cool it, a scum is formed, you get a thick scum over here, and as a result of which the uniformity of this gel is totally destroyed. So, what is needed is this evaporation has to be done under very, very controlled conditions. In the industry, there are many ways of controlling it, but they are all based on a simple lab model. When my students do this experiment, all they will do it, if this is the table, tabletop. They will take the gel in a wide Teflon vessel, pour the gel in, or the refluxed solution, and then simply cover it up with a bigger container. Nobody, we don't want a gas tight seal over here. What happens is, at first the water alcohol mixture evaporates, saturates this area, and as a result the evaporation rate of ethyl alcohol water from this surface becomes an equilibrium process. This is the simplest way of drying the gel and a very effective one. There are more complex ways of drying the gel. What industry does is, it has got controlled temperature, controlled humidity ovens. They look more like a refrigerator, but it's not like a refrigerator. What they do is, it is connected to a steam generator, and there are heating elements over here. They control the temperature through the amount of heat that is generated by these heating elements. The amount of steam controls the vapor pressure. And they have got series of these gel containers which are stacked inside it, and they are allowed to dry up very slowly. Now, these dried gels can be used for various purposes. They can be used for optical windows. They can be used for other purposes also. However, when I talk of thin coatings, I shall come back to this sol gel process, where I shall refrain from drying the gels in the vessel. All I will do is have a very thick gel and use that to dip coat other surfaces, but that is for the future. So, essentially, in this process what we have are strands of these TEOS gel, TEOS fibers, which are formed, and then during drying they get very densified, and then if we calcine, we get the required product. Now, this method of acid hydrolysis gives you polymeric chains, which is essential for many processes which I shall pick up during ceramic fabrication. However, should we want ultrafine powders, this alkoxide route is also eminently suitable. In that case, we do base hydrolysis. we would still take TeOS in water, add ethyl alcohol and 1 drop of 1 normal base and heat it. Here what happens is all these ethoxy bonds are hydrolyzed and we end up with SiOH4. And these then clump together to give you very fine particulates. There is this SiOH4, you dry it, you will get very fine particulates of SiOH4. If you heat it, you will get SiO2, very, very fine powders. Now, I was talking of preparing multi-component powders or multi-component ceramic oxides. Here I have talked of only tetraethyl orthosilicate. The reason I have done it is this alkoxide based processing route is also at times used for making multi-component powders. I have talked of preparation of magnesium nitrate, magnesium aluminate using magnesium nitrate and aluminum nitrate as starting materials. Magnesium aluminate can also be prepared by this alkoxide route. You see, why am I discussing so many methods for magnesium aluminate? Magnesium aluminate by solid state route, magnesium aluminate by spray pyrolysis route, and now I am talking of magnesium aluminate by alkoxide route. The reasons are many, and the most important one which I can think of right now is today we have to coat polymers with ceramic oxides for various reasons. One may be to make the polymer surface scratch resistant, but more than that, the world is increasingly looking to anti-reflection coatings. Anti-reflection coatings based on ceramics have been known for over 30 to 40 years and they are used extensively. But why on polymers? The simple reason is many of you are wearing spectacle lenses which are made from plastic. Plastic is scratch resistant. It needs to be coated so that it becomes scratch resistant and also anti-reflecting. All of these plastics, their glass transition temperature or they soften at very low temperatures, 130, 140 degrees centigrade, nothing more. And these ceramics, they are processed at much higher temperatures, thousands of degrees centigrade. But if a way could be found to have these ceramics deposited from solution on the plastics at low temperature, at temperatures lower than the glass transition temperature. That would be the technology answer to give you scratch resistance polymers, which can be also used for optical purposes and is got anti-reflection coatings. So, the drive has been how to deposit ceramic coatings on materials at as low temperature as possible. Now, if I simply take the case of magnesium aluminate, if I take magnesium oxide and aluminum oxide, mix them and calcine them, I will require temperatures close to 1500 to 1600 for them to diffuse into each other. And even then I will have to do the heating, calcination, cooling, grinding step at least 2 to 3 times. If I get magnesium aluminate from the solution route, they are still powdery. I have to devise ways to make them into thin films. But what if I could modify this tetraethyl orthosilicate process so that we have got an alkoxide gel of magnesium and aluminum. The advantage would be that it could be if we could synthesize the polymer having MgOAl, AlO-MgOAl network structure, linear structure, then what I could do is I could use the gel to coat any surface, and because the material is mixed in a total molecular level, I could fire it at much lower temperatures. That is the big advantage. This is exactly what was done. For example, magnesium methoxide, OMe2, plus aluminium isopropoxide, I would leave you, I will not say what is the structure of this isopropoxide. I leave it to you because there are some things you have to find out for yourself. So, magnesium methoxide, aluminium isopropoxide, these were dissolved in water, ethyl alcohol mixture. Ethyl alcohol was added, 1 drop of acid, and this was refluxed. If you remember, I used the term reflux earlier when I had boiled this solution so that with a condenser so that no liquid could evaporate. Once I do this, what I get is this mixture. You see, I have here got Mg and aluminum mixed in ratio of 2:1. Now, if I could hydrolyze it so that two of such chains if I could hydrolyze this product carefully so that I could have a straight fiber, I have got my magnesium aluminate. This, when heated, could be dried to a gel and then this could be used for coating purpose, like say dip coating. Now, what is this dip coating drying? I shall take up separately. Right now, I am focusing on synthesis of the ceramic powders. So, this alkoxide based process in certain cases has helped us develop coatings or powders of materials of two component systems. Usually, however, we are not so lucky. Our luck runs out very fast. For example, we have a major problem. One of the first things over here in this magnesium aluminate case, was the hydrolysis rate of magnesium ethoxide equaled that of aluminum isopropoxide. But in most cases, the hydrolysis rates are different. If I take the case of say TEOS and I try to take say titanium tetraethoxide, because titanium is a very industrially important product, this hydrolyzes much faster than TOS. This is a major problem. So, if I mix TOS along with titanium tetraethoxide and put it in that refluxing flask, I would see titanium tetraethoxide hydrolyzing very fast, TOS would not. So, in such cases where the industrial demand is very high, it is a very high value added product, what we do is allow partial hydrolysis of the slowest hydrolyzing material. Hence, in this case, we would take TOS plus water plus ethyl alcohol, hydrolyze, not fully, partially. And then to this add TiOET4, it's an ethoxide, that is why I said OET4, with vigorous stirring. You see, what we want here is SiO2 TiO, SiO, Ti and blah blah blah. This is what we want. We certainly do not want SiO, 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 Ti, OSI. We want a very, very homogeneous product. So, when I said allow partial hydrolysis of the slowest hydrolyzing material, add TeO, tetraethyl ethoxide with stirring, it is not that easy. Each step has to be calibrated, measured, and then the hydrolysis has to be done. It is only then we will get a homogeneous product, or else we will land up with a totally heterogeneous useless product.